Hey guys, Junkie the Monkey here. We finally made it. It's time to talk about circuitry and electronics. But before we can do that, we really have to understand current. And before we can understand current, we need to understand electricity. And so what we're going to do is we're going to initially start by talking about electricity and what it is. I don't know if you've ever tried to explain electricity. If you don't really have the low-level understanding of it, it's really difficult to explain. You can go out and look at a car and say that's iron or that's fiberglass. You can look at a tree and say that's made up of carbon. You can look at grass and all of the different things that you're familiar with seeing on a daily basis and generally have a pretty good understanding of what it is. But electricity is a little bit different, and it's kind of taboo, at least in the layman's arena. Nobody really understands what it is, they just assume that it's okay, and that it works, and that's all they really need. But when we start to talk about electronics and the different pieces that make it up and why we're doing things or how we're doing things, it's really good to have a firm understanding of what's really going on under the covers. And so we're going to start with electricity and kind of get an understanding of that so that we have an even footing when discussing circuitry. So let's go ahead and hop on into it. So I've just got Photoshop up here and we're going to use this as kind of like a whiteboard. But let's start explaining some things and start to get an understanding of what electricity really is. So as I was explaining before, when you look at something, and we can use the example of a block of metal, right? And we can say this is gold, even though this is a very bad drawing of a bar of gold. When we see that, we can associate it with something metal, something solid, something very firm, right? With electricity, there's no element. There's nothing that makes... I can't combine a bunch of molecules of a compound together and get electricity. So if that's true, then what exactly is it? And in order to understand that, we need to understand atoms. So let's take a step back. Let's think back in time a little bit to our science class and let's talk about some chemistry. All right. So we're talking about atoms. Atoms are made of a bunch of different things, but let's draw a simple atom here. This is a really bad atom. I'm no artist, and the artists on my teams would probably laugh at me, but we're going to go ahead and move on from that. This looks more like an egg, but that's okay. Now, an atom has a couple different parts. Inside of the atom, we have a nucleus. And the nucleus kind of makes up the basis of the atom. Inside of this nucleus, there are a bunch of different particles in here. And the particles that make up the nucleus are protons and neutrons. Now, for our purposes, neutrons are kind of irrelevant, so we're not going to spend a lot of time there. But something that is important are protons. Protons in general, when you say you want to look at the positives and negatives of something, you say that you want to look at the pros and cons. So if we use that, the positives of that equation would be the pro. So, kind of along the same lines there, protons would be a positive charge. Neutrons, think neutrality like Switzerland. Neutrons are completely without charge. They have none, right? And then electrons, which we'll talk about a lot here, but electrons have a negative charge. So in the nucleus, protons and neutrons exist in harmony. the amount of protons inside of an atom helps us to identify what type of element it is. As an example, copper is used in circuits a lot, and copper is identified as an atom that has 19 protons. And in general, an atom will have the same number of protons as neutrons. Just as a note. Again, we're not going to go too much into detail about the relationship between protons and neutrons and what neutrons do, or any of that. But just remember that the amount of protons determines the element. Okay, so we've talked about protons and neutrons and the nucleus and all of this other magic stuff that seems to exist. But what about electrons? So we mentioned this here, but we haven't yet described it. So let's take a minute and explain what electrons are. In an atom, there are a number of tracks that electrons can follow. And these tracks kind of work very similarly to how you would imagine planets circling the sun. So there are a number of different rings, and electrons in general flow through these rings. They're constantly moving. They move at the speed of light, so they're very, very fast. And the outermost ring is something that is pretty interesting. So the outermost ring is called valence ring. And electrons in this are really far away from the protons that are kind of binding the electrons or kind of drawing the electrons in, right? Very similar to gravity. But the valence ring is really far away from the protons that are drawing the electrons in. And therefore, the coupling to the atom is extremely loose. Given enough force, right? So if we were to hit Pluto, which isn't a planet apparently, with an atomic bomb and create an incredible amount of force, we could force it out of orbit of the sun. Very similar to that, an electron exposed to enough force could be forced out of the atom. This creates a free-flowing electron. And essentially, electronic systems take advantage of this phenomenon. So, if this guy were to escape out here, now this is a free-flowing electron. Now, any other atoms in the area that essentially were open to accepting this could absorb this electron and then have a positive or negative charge difference based on the fact that it took in that electron. And this whole concept is why we're able to create something that is a current or power. And we'll talk more about this, but let's just erase our board here and take a minute to expand a little. So make sure if you want to copy any of this down, you do so. Pause the video. All right. So that makes sense, right? We have these things called electrons. They have a negative charge. They can escape the confines of an atom, like Sirius Black escaped from Azkaban, you know. But what allows us to create this magical thing called current? So we'll talk a little bit about conductors here. And conductors are a really, really interesting concept. So atoms are more or less likely to absorb electrons and more or less likely to allow electrons to escape its valence. This interactivity or this correlation creates conductivity versus how much of an insulator something. So when you look at a wire, right, and we'll use the example of a copper wire here. I apologize for my terrible artwork, but it should at least create some entertaining situations for you guys while we're talking about things that a lot of people I know find boring. But if we have a copper wire here, you very rarely see copper wire just, hanging around in your house. But your house is often made up of some kind of conductor. Copper used to be used a lot because it has a very high susceptibility to absorbing or allowing electrons to escape. But it's typically surrounded by something called an insulator. And this could be rubber, it could be some kind of braided compound, something that does not absorb electrons or allow them to escape. These insulators allow us to create a direction with a current. So it allows us to create bounds that electron chain cannot escape. So that means that whenever we pass a current or a stream of electrons through this wire, this insulator is also helping to make sure that it's not absorbed by something else that might be, for instance, touching this. Cool. That all makes sense, I hope. Let's move on. So an electron can be forced out of an atom by exposing it to force. How does this relate back to electronic systems? Well, let's take a minute and look at a common concept that's used. And I'm going to draw something. If my art is bad, I'm sure that you'll understand what I'm drawing here. All right. So we have a very bad light bulb. And we always use the light bulb as an example because it's one of the most simple forms of a circuit. So if we pass, say we have a little wire here, and we pass an electrical current through this, a light bulb will accept the current in one of its connectors and pass it through a circuit, and then the current will continue out of the light bulb. Is that we've created a closed circuit. And a closed circuit is basically just a circuit that has a point A, a point B, and it kind of creates a loop, right? It creates a closed circuit with a power source. Okay, so in the case where we're using a battery, the battery is providing charge, which then powers the light bulb. There are also some discussions about alternating current versus direct current, but again, our idea here is to explain only the things that we really need to understand to be able to talk about circuit. So in this scenario, electron stream is being forced into the light bulb. That is going through the different pieces of the light bulb and creating heat in the case of an incandescent bulb. Or that charge is creating some kind of vibration, which is creating light. Why do we need to know this, right? There are a number of different pieces of a circuit. Inside of a circuit, you typically have a power source, which is responsible for creating charge. You also typically have different components. Some kind of sink, right? In this case, our sink is our light bulb. But you can also have a couple different other things. A capacitor, often dictated with these two lines here, its responsibility is to store charge at the junction point, but not allow the current to pass through until a situation occurs where the positive and negative charges are not equal. As an example, say our battery goes dead. If you've ever noticed, if you lose electricity or if your battery goes dead in a video game console controller, it doesn't just die immediately. That's what a capacitor does, is whenever the charge is lost, it now allows the current to flow through and create that current again for a few seconds. And that characteristic is why you'll see that even after a power source is completely dead, your electricity goes out, but your device doesn't die immediately. It kind of has a couple seconds there. And that's what the capacitor does. It regulates flow even with an inconsistent power supply. And we, again, won't go too much into detail there. All right. So that's all fine and good. Let's go ahead and erase again. And again, these things are not exactly correct. We're just trying to create a basic understanding of how these things work. All right, so let's talk about switches. So switches are actually what we wanted to get to here, and they are the part that is super important in terms of circuit in the next conversation that we're going to have in relation to binary. So in a circuit, we have the ability to turn things on and off. Something like a light bulb, as the example that we were using, has a switch that allows you to flick it on and off. That's caused by a very simple switch in a circuit. Now, in electronic systems, you're going to have a bunch of these, and they all do different things. So if we look at, very quickly here, a more complex concept, let's say that we have a phone. In your phone, which does a number of different things today, it's got a camera, it has a screen, it has a number of different LEDs, it has buttons that allow you to turn the sound on and off. It does a number of different things, and all of these things in the circuit world are caused by switches. So at a very simple level, let's assume that this is the camera circuit. You're going to have your power supply, which is going to lead to whether or not this thing has a current to the camera. Now, you're not always using the camera. The camera is not always active, and the reason is because there is a switch in there. Somewhere in the chain, in this very incredibly complex circuit, there is a switch, and this switch is either on or it's off. And at the very base level, this is what defines whether something is functioning or not. Whether it gets a current, whether it is currently active, is determined by a switch. And this will become extremely important later when we're actually in the next lesson when we're talking about binary. Because a question that I get a lot is, why was binary chosen as the basis for transmitting data or performing functionality in software systems? And ultimately, the most baseline simple answer is because of the nature of circuitry. Circuits can power something or not power something based on whether a switch is on or off. That means that you have two values, two possible values, right? A switch can't be partially on. And because of that very simple characteristic, you can think about computer systems in a very similar way. I want to signify whether or not I have something or I don't have something. And basically anything can be justified in that way. You can ask or answer almost any question with a yes or no answer, and it will relatively make sense. Even if it's not the most ideal answer, it will answer the question. Now, that means that in our circuits, I can now directly relate the value of a switch to some kind of action or data somewhere. That makes a whole lot of sense. This is the whole reason that we wanted to talk about circuits and current, is because we wanted to establish the relationship between the circuitry and our software systems. So now I hope you're starting to realize that because of the nature of circuits and switches is actually the root reason as to why binary was chosen as the system that is the basis for modern computing systems. There are many more additional reasons to why binary was chosen. It's the simplest possible number scheme that has some kind of value. And there are a number of different arguments to be had for that. But at the very root level, the fact of the matter is, circuits operate on a set of switches. Those switches are either on or off, and therefore having the ability to have only two possible values for something means that we can directly relate something in our software system with the underlying circuit. That's all we have to talk about on this topic. Again, I didn't want to go too much into detail. Maybe later on we'll create a video that dives into the electrical systems a little bit more. Valuable now, as embedded systems are becoming more and more important, and programmers are kind of expected to understand the circuitry that they're building for. So maybe we'll create a video later on this topic and go into a super deep dive. But for now, this should suffice to get us a basic understanding of what circuits are and how they relate to software. So I hope you guys are walking away from this lesson with a little bit more information. I know we didn't dive a whole lot into some of the specifics there, but as I said in the overview, I want to make sure that everybody has a good understanding of the core concepts moving from piece to piece, so that when you look at some of the future lessons, you'll at least understand where we're coming from and where computer systems came from to start with. I really appreciate you guys taking the time to watch. Make sure that you like and subscribe below if you liked the content here, as that will give you a way to be notified whenever new videos are posted. We'll be posting about a video per week. For now, till next time, thanks for watching, thanks for joining in.